Good evening, everyone. Welcome to Physics with Keith. It is Tuesday. It is 6 p.m. And if this is your first time tuning in, then the way this works... Hi, Freya. The way this works is that you can interact with me live throughout today's tuition session by getting on Discord. The link is in the description to this live feed. So get on Discord, and then you can type into the Discord chat. There's a link on the main general channel to the correct channel to go to. Or you could just follow the link within the description of this video. It should take you straight there. And you can see there's plenty of regulars. Oh, I'm pointing in the wrong direction. That way. There we go. Plenty of regulars are joining in and saying their hellos and stuff. So it's good to see you all again. Last week, we looked at gas laws. And we had an introduction to gas laws and the experimental gas laws. We didn't look very much at the ideal gas law. Well, my. Okay, kid, thank you very much. Don't know how I should take that, but I'll take it anyway. Okay, so today's lesson, what I want to do is look at those gas laws in a bit more detail, and we're going to push into A-level territory now. But don't worry, this is still accessible to GCSE students, and where there are things that are strictly A-level, I will let you know. And if there are equations, for example, that you'll need to know that you don't know because you're a GCSE student, I will let you know them, don't worry. So I've used my usual bank of resources. That is to say, well, that's one of the equations. That's right, arcanic. Arcanic? Arcanic. I'm going to go with arcanic. Tell me if I'm pronouncing that wrong, please. Yes, so I'm going to use my usual resource, which is OCR, who, when I contacted them, were very kind and told me that I could use... That's great, thank you. They were very kind. They told me that I could use their exam questions as long as I gave them credit and made it a few things clear. First of all, OCR has not seen any worked solutions that I might give. And secondly, they don't endorse any worked solutions I might give. And thirdly, I have to give them credit, so I've done that. These are all from OCR. Exactly, OCR is very generous. I won't say ill of the other exam boards, but they were explicitly... they explicitly denied that I could use their questions. So anyway, so we've got this first question here, which has come from the Foundation Tier Paper 1 for the GCSE Gateway course. This is from the sample papers. And the first two questions we're going to look at are multiple choice, and I think they should be quite straightforward, really. So what I want you to do is to have a look at this question, decide whether you think the answer is A, B, C, or D, and then I'm going to ask you to vote for what you think the correct answer is. Now, if you give me a few moments to mess around and type the voting thing into Discord while you're trying to work out the answer. So don't vote for anything until I say vote now. So, question 4. Don't vote for anything yet. Don't do it yet. I'm now going to fight with my inability to use technology. So let's use red to mean A. Let's use, look at this is seamless. Blue to mean B. There's probably an A, B, C, or D already, isn't there? Let's use... Don't vote yet. Green to mean C. Why am I attempting this? And let's use... I'm running out of colours. Let's go with yellow to mean D. There we go. There is an A, B, C, D. I thought there would be. Okay. Well, maybe next time. Okay, so vote now. Do you think it's A, B, C, or D? Where rather perversely A is... Yes. Yep. I could do, Joe. That's how I got the red, blue, green, and yellow. I used the search. And I didn't think to search for the letters. That's pretty special, that. Okay, so it looks like almost all of you are going for C. Yeah, I have been known to throw things, kid, although I try not to throw them at people. And I have been known to wear sandals. Maybe we're the same person. The letters at the bottom of the section. Okay, I mean, I'm not going to hunt for them, Pranav. Okay, so it looks like everyone's going with C. How does the pressure and the volume of the air change if I push the syringe inwards, well, the volume is going to decrease, so we know it's either A or C. We can eliminate B or D straight away. And if the volume decreases, the pressure increases because they're inversely proportional, and we looked at that last time. So if we wanted to, we could get my little pen out, and I'm going to do it. I'm going to pretend I'm doing this question, and I'm going to write in C. There we go. So then the next question. The sealed can contains gas. The can is heated and the pressure of the can increases. How do the particles cause the pressure to increase? So make a decision, but don't vote yet. And I will attempt this again, this time with the letters A, B, C, or D. Shall we see what happens? So this is question 10. Don't vote yet. A, there's an A. It's a red A. Maybe I didn't want that. B, there's a B. I'm doing it. C. Oh, it's a blue C. There's no red C. Right. Note to self, next time only use blue letters. Okay, vote. Okay, so it looks like most of you are going for D. One of you went for B. Now, the particles can't expand. That's definitely not what happens. Particles do not expand. It is true that if I have a fixed quantity of gas in a vessel where the volume of the vessel can change, and I increase the pressure such that the volume... sorry, should I say that I increase the temperature or something, the pressure increases, and then the volume increases in response to that, then what would happen is the average distance between the particles would increase. That is true, but that would be to reduce the pressure again. That's what happens in real life. The pressure would then reduce because the volume would increase as you increase the temperature. But what we're talking about here is a sealed can. So this is a can that we're going to assume it can't change its dimensions. It's the same volume. Sealed can, not a syringe or a plunger or anything like that. And it's heated up so the temperature increases, the pressure of the can, the gas increases. Yep, that sounds reasonable. But the volume we're saying is kept the same, and the quantity of gas. I don't know. I didn't unvote for B, so I don't really know what happened to that, Pranav. How very curious. Fascinating. Oh, it's just appeared on the right-hand side. Okay. So, no, I think you've all got it. The particles hit the can more frequently. Great stuff. Okay, so we're going to move on now to question 11, hopefully. Oops, I've scrolled too far. You can see all the fun questions we've got coming up. Question 11, last one of these quick multiple choice questions. These quite straightforward GCSE ones. This is a maths one. Again, don't vote just yet. Let me get the answers all queued up first, and then you can vote. Right, note to self, use the blue letters. There's probably some bot that can do this more quickly. But I'm not that sophisticated. Okay. Go for it. Vote for it. A basic understanding of pressure. Do you know what pressure means? Vote, vote, vote. Okay, so I think someone voted for D or something, but they've changed their mind since. Yes, the answer is B. 40 divided by 0.5 is 80. It says they're all wrong, though. Can you explain to me why they're all wrong, Pranav? Right, but there's no indication that this is in air. Also, we don't know if this 40 newtons includes the component from the air. So you're making quite an assumption that 40 newtons could contain that, include the component from the air as well. Yeah. Thank you very much, Duck. So let's move on to some more involved questions. These are A-level questions. Now, if you're a GCSE student, I really urge you to... No, we're all good friends. Don't worry about that, kid. Pranav often corrects me when I make mistakes, so it's only fair that I get to return the favour from time to time. So, question 20 here. It's probably quite small for you to see. I can possibly bigger it. There we go. Hello, Avax. It's good to see you again. Avax1 USS. I'm glad you could make it. So here we've got a question that's an A-level question. It's from the OCR A-level Physics A. And this is one of the sample questions. This is question 20 from the sample paper 1. And the code is there if I need to include it for copyright reasons. So 20A, we've got some apparatus. And there's a conical flask filled with air. And it's a sealed vessel, the volume can't change, with a pipe, rubber tubing, connected to this manometer labelled pressure gauge. And there's a thermometer in the water, so this thing over here is a water bath on the left. Let's get my hand out so you can see my cursor. This is a water bath on the left. And we're heating it with a Bunsen burner, which is going to provide a pretty steady power into the water. It's not going to be perfect, but it'll be okay. So it says, describe how this apparatus can be set up. I don't know how to answer that. and used to ensure accurate results. Okay, so describe how this apparatus can be set up and used to ensure accurate results. Now, remember, I don't know if you've been here before, if this is your first time, but regulars will know this. I do not look at the mark schemes in advance. Okay, yeah, may have been sent to the wrong place there, kid. Yeah, I assumed that. Avax, so you're talking about how to change this particular experimental setup to improve the accuracy. And I think, yeah, we could go, if that was what the question was asking. So just a bit of background. I don't look at the mark schemes in advance because I don't like the idea of just tutoring people to pass exams. There's plenty of people out there that will do that, memorize a bunch of mark schemes and think that means that you can do physics. It's wrong. You can't do physics by memorizing mark schemes. Mark schemes are useful when you are at the final stages where you're learning the exam board idiosyncrasies that's going to get those extra marks. But at the moment, unless you're about to do an exam, really you want to focus on understanding the physics. And that's why I'm not looking at those mark schemes. So 𝗂𝗏𝗃 is saying that we can repeat any measurements we take. Yeah, I mean, that might be how we use things to try to improve accuracy. Taking repeats will reduce the uncertainty in our measurements. Yeah, well, exactly. Exactly. No. You just learned a mark scheme and you don't know any physics. I agree with you, kid. Absolutely. So what can we do to make sure that we get more accurate results? Can anyone think of anything? We've got a few examples come up here. Pranav says it's the flask sealed with a bung. I think that's the case, yeah. 𝗂𝗏𝗃 has said use a thermometer with more increments. Well, that will improve the resolution of the instrument, which will improve the precision of the temperature. But if our temperature is a range from 20 degrees to 100 degrees Celsius, that extra precision probably isn't going to help us very much. It's not going to be that important. Yeah. So, Avax, you've said the same thing. So use an electric heater, variable heat outputs. Maybe you've got an electric heater where you've got a voltmeter and an ammeter and a stopwatch so you can determine exactly how much energy you put in. Is that useful in this particular apparatus? Actually, probably not. Read what the investigation is. The variation of the product PV with temperature. So does it matter whether or not we heat it at a constant rate? There's no time in there. Time doesn't appear in there. So the thing about making sure you've got a better heater, that sort of thing, I would say no. So make sure as much air is submerged as possible so that more of the air is heated. James, I think that's a good answer. You're going to want to make sure all of this conical flask, or as much as possible, is immersed in that water bath. That's a good one. Make sure the inside flask is underwater. Yeah, which is what Pranav's just said as well. A larger pressure range. Now, there's an issue with this. You don't get to choose the pressure, Əkānik. It's decided for you by the universe. You change the temperature and the pressure will change as a consequence. The pressure is your dependent variable. The volume is fixed, but the pressure is your dependent variable. So you're not really going to have any direct control over that. Hello, Wombat. It's good to see you. So ensure the Bunsen flame is close to the beaker. You see, now that first point, Wombat, I would say doesn't really matter because all we care about is pressure, volume, the product of pressure, volume, and temperature. So we don't care about how it's heated, how quickly it's heated. But what we do care about is your second point there. You've said make sure the thermometer... It happens, don't worry about it, Wombat. You said the second thing, you said make sure the thermometer is swirled around. We wouldn't use a thermometer for that, would we? That is a quality song, kid. Yeah, we wouldn't use a thermometer, especially if it's a mercury thermometer, because we risk accidentally banging it into the flask and it breaking, a mercury spill, and then my technician will tell you, because I did a rather nasty mercury spill a couple of years back, and then she had to help me clean it up, and it was a mess. So, no, we wouldn't use a thermometer. We'd use a glass rod, as Əkānik has said, or Pranav has said, or Avax has said. We'd use a glass rod to stir it up, yeah. What else? Oh, it's a mess, isn't it? So this is quite an important one. You don't actually want to heat it up too quickly because the temperature of the air will not be the same as the temperature of the water as you heat it up. You have to wait for the air and the water to reach equilibrium, thermal equilibrium. The slower you heat it, the closer the temperature of the air and the water will be. So we don't want to move the Bunsen burner closer. We don't want to turn the Bunsen burner up. We don't want to heat up the water rapidly. We want to do it slowly, allowing as much time as possible for the air to reach the same temperature as the water. It won't reach the same temperature, but it will be closer to the same temperature if we heat it more slowly. And I think that is a really good answer. So heat it slowly, stir the water. And then it says describe, so we don't have to say why that will help. Okay, let's move on to the next. I'm not going to write an answer because you all know my handwriting is fairly terrible. So let's move on to part B. An investigation similar to that shown gives measurements of the pressure and the volume and the temperature. So we've got now plotted pressure multiplied by volume. That looks suspiciously familiar. I think one of you stated an equation earlier on with that in it. Atmospheric pressure is not zero. That is absolutely true. And then temperature on the x-axis measured in degrees Celsius. And I suspect, Avax, you've spotted that already. So the results in the plotted graph, blah, blah, blah. Explain in terms of motion of particles why the graph does not go through the origin. Any thoughts? And I'll let you type your answer. Let's have your thoughts. So, Avax, what you're doing there is just reframing the question and restating it. You've said atmospheric air pressure is not zero when atmospheric room temperature is not zero. I think I know what you're saying. What you're saying is, look, the pressure isn't zero when the temperature is zero. Well, yes, I know that's true because that's what the graph says. The question is explain, and then this extra bit on the question, you've got to read it carefully, in terms of the motion of particles. I'm afraid I can't remember, Wombat. The sort of thing I should have written down, but I'm afraid I can't remember. But we'll see how many marks we can get. Yes. And physics R, we could go into loads of detail about that, couldn't we? We could talk about conservation of momentum. It's all right, kid. I do it for pleasure. It's good fun doing physics. Ah, 𝗟𝗲𝗲, it's good to see you. Oh, I must make sure I switch you across to a regular user. Yep. So, yep. So, yeah. I mean, that's a pretty good answer, actually, 𝗟𝗲𝗲. But what we could say is that the particles exert a force on the walls of the container when they collide, because the walls of the container exert a force on the particles, changing their momentum. And we could go as far down that as we want to go. But I think that's probably the wrong direction, because it asks for it in terms of the motion of the particles, not in terms of their collisions. So, Pranav, I like your answer there. You've identified that at 0 degrees Celsius, the particles are still moving. That's very important, which means they are still colliding with the walls of the container. You said with the flask, so that's okay. Colliding with the flask, and therefore there is still a pressure. I like that. So Avax says sea level atmospheric pressure particles in the air have a non-zero amount of kinetic energy. That is true. But we're not interested in the kinetic energy. We're interested in the motion of the particles. Be really careful what you're being asked for. So the pressure recorded would be above 0. As pressure is measured by the collisions of particles. Well, it's not measured by, but it's caused by the collision of the particles with the container. Not quite, kid. So you've said there the temperature increases, kinetic energy of the particles increases. That is true, and that will probably come up later. But remember, we're interested in the movement of the particles, the motion of the particles. Always keep in your head what the question is asking for. Yeah. So things to be cautious of, and this is especially for GCSE students as well. Pressure is not caused by collisions between particles. Don't say that. Don't say that collisions between particles causes the heat to be created or things like these. They're all answers I've seen students say. They're all incorrect. Pressure is caused by the particles colliding with the walls of the container, then being deflected, so they travel in the opposite direction. That means there's a change in momentum with those particles. Therefore, those particles have been pushed by the walls of the container. And if the particles are pushed by the walls of the container are pushed by the particles. That's Newton's third law. So Wombat said they don't have any kinetic energy, absolute 0. I don't care about their energy. Therefore, no volume, no pressure. Okay. So Wombat, you're giving me an answer there in terms of the experimental gas laws. The experimental gas laws assume that gas is a continuum. But this question says, in terms of the motion of particles. That means we really do need to break it down to what those particles are doing. When we get to that scale, we can't use those experimental gas laws. They don't apply anymore. You've also gone on to say that particles are still moving. Yeah, we all agree with that. Yeah. Having kinetic energy, I don't care about their energy, I care about the motion. And they collide with the container, which creates pressure. I don't like creates pressure. I don't like that terminology. Creates pressure. There is a pressure because there is a force acting on that surface. The motion of the generates pressure. I don't like it. There is a pressure. I don't think you need to say creates. Exerts pressure. I'm not sure if I'm happy with that either, Pranav. You can exert a force and therefore there is pressure. And you get away with that sort of thing. Maybe I'm getting bogged down in semantics. You know, it's a side effect of having an over-analytical brain. The collisions are elastic with the walls of the container, Wombat. That's what we care about. There are elastic collisions between particles, but I don't care about them. Okay. I think this question we've had as much mileage as we can. The key ideas were at 0 degrees Celsius, the particles are still moving. And you can say they stopped moving at negative 273 degrees Celsius. So you've given up some more information there. The particles move at any temperature above negative 273 degrees Celsius. Therefore, because they are moving, they will collide with the walls of the container. And when they collide with the walls of the container, they will exert a force on that container. So there will be a pressure on that container. Yeah, I mean, I like what you've said there, kid. I like what you said there, but we're working backwards because we're going down to 0 rather than looking forward. But what you've said isn't wrong. Right, I think we've had enough mileage out of this question. Let's move on. And we're going to have to flip back to the graph, I'm afraid. These two questions, you're not going to be able to answer this just by itself. So what I'll do is I will grab this and I will try to put it so that you can see this question and the graph at the same time. There we are. You don't need the description. There. You can see this is specimen paper because the word specimen is there all cut up. So it says the mass of the gas particle is that, calculate the mass of the gas, and then calculate the internal energy of the gas. This is well and truly A level. So I'll give you a bit of time. Now, if you're a GCSE student, you're now thinking, I haven't got a clue. Oh, no. Oh, that's terrible, kid. Well, you can always watch it while you're going home on your phone, as long as you don't get mugged. No, I would say you don't have to find the gradient. You could do it finding the gradient. But given that it's a straight line and we know it's going to pass through the origin, we really don't have to. Right, so for GCSE students, the equation we're going to use is this equation. I've just posted it there. P is pressure. V is volume. So P times V is pressure times volume. N is the number of gas particles. K is Boltzmann's constant, and we can take that to three significant figures as 1.38 times 10 to the power of, I can't remember what the unit is there, 1.38 times 10 to the power of minus 23. And T is the temperature. But GCSE level students, there's a sting in the tail for temperature that you might know about. It is GCSE level. Anyone want to let me know what that's R. That's the ideal gas constant. That's what you use when you're counting the amount of gas. Yeah, exactly. That's what you use when you're counting the amount of gas in moles. So 値々has just asked about a different constant that we use. Also, 値々will use 273 degrees, 273 Kelvin rather than 273.15. We don't need to go to that sort of precision. Exactly, Wombat. Exactly. This graph will pass through the origin only if your temperature is measured in Kelvin. We don't want to work in terms of moles. We want to work in terms of molecules because we know the mass of each molecule. If this is the mass of a molecule, then the total mass is going to be the number of molecules multiplied by the mass of one molecule. The total mass of people in an elevator, or as we call it, a lift, is equal to the mass of each person multiplied by how many people, with the assumption that all people are identical. Oh, Pranav's breaking out the rather broken bot for text. The LaTeX bot that never quite works. Well, let's work it out together, shall we? Because it might be right. So I've got my pen out. The mass of the gas. We're going to start by saying that PV equals NKT. And I'm going to divide through by KT. So I'm going to say that PV divided by KT is equal to N. So the mass of my gas is going to be the mass of one particle, which I'm given here, multiplied by the number of particles. That's the mass of one particle multiplied by PV over KT. So let's pop some numbers in here. 4.7 times 10 to the negative 26 kilograms multiplied by, now pressure times volume. What I'm going to do is I'm going to use this number up here. And reading across, I need to be careful of this scale. 1, 2, 3, 4, 5, 6, 7 tenths of the way between 2.5 and 3. All right, well, let's work out what that is. 7 tenths of the way between those two is going to be 2.85 times 10 to the 2. Whee! I think that's what you just noticed there, Wombat. This is GCSE. They will trick you at GCSE with this as well. They will trick you with that, although they won't necessarily represent the label on the axes quite like that. So let's type that into our equation. 2.85, 285, divided by, now I need my constant, and the gas constant I gave you before, I put it into the chat, although it's disappeared up the top of the screen, so I'm going to have to look it up again. 1.38 times 10 to the negative 23. And then we're also dividing by temperature. But we have to be a bit careful, because temperature is not going to be 110 Kelvin. It's going to be 110 plus 273. We need to get it in Kelvin. Okay, it looks like everyone's getting the same answer, so I shan't embarrass myself by typing it into the calculator. Actually, I will. I'll put it in the calculator. I enjoy a good bit of calculator action. Big fan of using my calculator. Today, I'm using the 𝗵𝗵35S. Oops. 𝗵𝗵35S. Thought I'd mix it up a bit. That, and I left my DM42 at work by accident. But people who know me know that that will not be a problem. I have plenty of calculators. Okay, so who got 2.53, let's say 2.5 grams? Oh, it's in kilograms. Okay, who got 0.00? Let's do standard form. Come on, you're better than this. Who got 2.53 times 10 to the negative 3 kilograms? Yay! Good. And we'd give our answer to two significant figures because this is given to two significant figures. So our data can't be, our final answer can't be given to a precision greater than that. Now, GCSE students, you're going to get spooked by this, but let's pick out the things that are relevant to you. Converting the temperature, that's relevant to you. Spotting the funky scale, that's relevant to you. Being able to rearrange equations. Okay, so it's not an equation that you'll be given or that you need to use, but that doesn't matter. Being able to rearrange equations is relevant to you. And the problem-solving element. If you know the mass of a particle and you know how many particles, then what's the total mass? That is a GCSE skill. So really, the only A-level bit of it was using this particular equation, and you get given that on the data sheet. Wow! A-levels are easy, he says slightly sarcastically. It should be, no, you shouldn't. It should be 2 significant figures. Did I say 3, Wombat? My apologies if I said 3. I wrote 3, but then I thought I'd said you can only give your answer to 2 significant figures because 4.7 times 10 to the negative 26. No, it's 𝗬𝘳, they're not that easy. They really aren't. What I would say is that they take a lot of study, time and effort, but when it clicks, then it's straightforward. That's not the same thing as easy. I'm not saying it's easy, but there's no mystery to it. It's not one of those subjects where you walk out of an exam scratching your head and thinking, well, was that worth a mark? Did I get that right? Once you can do it, it's straightforward. And practice and putting the time in is how you master the skill. Yeah. So let's have a look at the next question then. Well, that's true, 𝗬𝘳, except sometimes it's not. For example, in quantum physics, we tend to deal with probabilities, but I'll leave that there. And in fact, you'll see an example of how physics doesn't use definite numbers today. It's one of the questions we're going to be looking at. So internal energy of the gas. So GCSE students, there's a new equation that you need to know, which I'll type. No, I won't type it into the chat. I'll write it here. And that is that the average kinetic energy of a particle in an ideal gas is equal to 3/2 multiplied by K multiplied by the temperature. Yeah, not today, Pranav. You know I love quantum physics. Okay, so you may, GCSE students, have heard it said that temperature is a measure of the average kinetic energy of the particles in a system. And is a measure of is a really weird, vague, wishy-washy way of saying that there's a relationship there, but it's not equal to. Temperature is not equal to the average kinetic energy of the molecules in a system. But there's a relationship there between them. And for an ideal gas, this is the relationship. Other substances have a slightly different relationship. And A-level students, it's this number here that changes. Or you could add other terms onto this as well. Basically, it's the number of degrees of freedom. But yeah, Pranav, basically what happens at university level is you stop using easy algebra and you start using matrices, and all of a sudden vector multiplication becomes tremendously important and things like that. But you know, if you can do it in A-level maths, you can do it in physics. Yep, great. 𝗬𝘳, you've seen this equation. That's super. So, anyone got an answer yet? Yeah, this is a kinetic theory equation. That's right. Okay, so answers are starting to appear. I need to go find my constant. Where's K gone? I can never remember my constants. I'm a physicist because I don't have to remember things. That works. And then 3/2. Okay, so a lot of you are giving me the average kinetic energy of a molecule. 7.7 times 10 to the negative 21 is the average kinetic energy of a molecule. But that's not what the question asks. You must be careful with this. We want the internal... Oh, that's a dark colour. We want the internal energy of the gas. Yes. Now, the reason, Wombat, why that works... Yes. The reason why that works is because there's no potential energy component in an ideal gas. Possibly 𝗂𝘃𝐸. I can't remember what the number of molecules was. Well, I don't even think I bothered calculating, did it? Did I? Whoops. So possibly, whatever that number of molecules is, don't make me work it out. Yeah, but I didn't bother working it out. I calculated the mass. I didn't do the intermediate calculation. I should have read ahead. What a fool. Yeah, so internal energy is made of two components. There's two things that come together to make internal energy. Internal energy, and I'll just use IE, that's not an official, that's Internet Explorer. No, that's not an official notation. That's going to be the total kinetic energy and the total potential energy of all of the particles within our system. But in an ideal gas, there's no intermolecular forces. There's no internal vibrations. There's no potential energy store. And that's why the total kinetic energy is equal to the total internal energy. So we multiply the number we've got there, whatever it was, 7.7 times 10 to the negative 21. We multiply that by the number of molecules, which I can't remember what it is. Wombat's giving it to me there, 5.3 times 10 to the 22. And you get whatever it is. I don't know. That's assuming Wombat's calculation is correct. I haven't checked it. I will. If you want me to, I'll do the calculation. You're going to make me do the calculation, aren't you? Okay, let me do the calculation. So 285, enter 1.38 E23 minus divide 110, enter 273 plus divide. I didn't get that as the number of particles. I'll do that again, Wombat, because you've got me worried now. 285, enter 1.38 E23 minus divide 110, enter 273 plus divide. Oh, yes, I did. I must have made a mistake with my calculator. That's okay. These things happen. You had me worried for a minute. Right, so 417. We wouldn't write 417. We'd round it. We wouldn't round it to 410. Oh, you're so funny. Funny stuff. So what I did there, 𝗂𝘃𝐸, is I just typed into my calculator this part here. That's the number of molecules. Okay, so moving on. Next paper. This is all OCR. Again, they've not endorsed my work solutions. They haven't seen nor approved, but they have given me permission to use them. This is from the 2017 June series. This is the Physics A spec, and this is paper 1, and there's the paper code if you want to look it up. The modelling physics paper. And we've got some more gas law stuff, and I really like this question. So I think it's the last question I've got on the list. Yeah, but it's a good question. There's a lot to it. So we're going to rattle through some of the early parts of this question. So, similar sort of situation. We've got gas in a sealed vessel, a pressure gauge, a manometer, and a water bath. It's heated using a water bath. Temperature is increased from 5 degrees to 70 degrees Celsius. The temperature of the water bath is assumed to be the same as the temperature of the gas. Okay, maybe that'll come up later. Who knows? And then we've got some numbers here. And it says, describe and explain how the student may have made accurate measurements of the temperature. And we've talked about this before. Stirring. Making sure you stir the water to get even distribution of temperature. Waiting long enough for the gas temperature to be equilibrium with the water temperature. You can't measure the temperature of the gas directly in this experimental setup. all you can measure is the temperature of the water. And theta is it defined in this question? Is the temperature of the water. So it doesn't matter. So we want accurate measurement of temperature. We wait until the temperature is still. Now, this is an important principle. When you're making any measurement, you make static measurements. You're measuring volume of a liquid, volume of water, for example, pouring into a measuring cylinder. The water's got to stop pouring before you measure it. You never make a measurement. You never measure a quantity which is changing, with the possible exception of time, duration. You can't help but measure that, because we live in a world where time keeps marching. Anyway, so I think we've covered A. I think we can move on from that. But this is, I really like this question. Again, this is A-level, but GCSE students, you're going to like this. Why is it sensible, looking at this manometer scale, why is it sensible to use this peculiar, archaic unit, PSI, pounds per square inch? What kind of crazy country would still use pounds per square inch to measure pressure? Well, there are times when it is sensible. For example, if I've got this particular manometer, yeah. So Wombat says greater precision. I like your answer, although we'd probably say greater resolution, Wombat. We can write our number to a higher precision because we have a higher resolution instrument. But I suspect at A level, we're going to have to go a step further. We're going to have to explain to the examiner, convince the examiner that we know what resolution is. And so I prefer 𝗟𝗲𝗲𝗲's answer there. Smaller spacing. I prefer that. I think that's a better answer. And I would say both. I would say the pounds per square inch. Yeah, I mean, they would both have the same parallax error, I would suspect. 𝗭𝘁𝗧, what you tend to find is there'd be a mirror behind the scale, and you'd line up the needle with the image of the needle in the mirror. Don't be spooked. This bit you see here is just a shadow from the photographer. That's not the image from the mirror. So you'd see or you might have a strip of mirror going around just around the outside, and you would line up the needle with the image of the needle, and that way you reduce parallax error. But on this display, we don't have that. That's not there. Or if it does, you can't see it. I genuinely watched a YouTube video today where someone photocopied a mirror. That's how low I've sunk. Anyway, so so the nearest PSI can be measured, but the nearest 10, yeah. Yeah, I wouldn't go actually quite as far as that one, mate. You've gone too far the other way now. Because the interval of 1 PSI compared to the interval of a kilopascal, you've got to do a comparison, or 10 kilopascals. You've got to do a comparison there. You know, you can say about 340 kilopascals is about 50 PSI. That is what it is. But the point is, the notches are closer together on the PSI scale, so I can record a number to a higher precision. Well, after I've done a conversion. It's a high resolution scale. Yeah, Pranav, it sounded cool, and I had to watch the video all the way through. It was a massive disappointment. So, moving on. Student made a reading of pressure of 37, give or take 0.5, pounds per square inch. What a peculiar unit. Complete the table for the missing pressure. And the pressure on the table is in kilopascals. So what this question is asking you to do is to convert from pounds per square inch into kilopascals. Something that you've probably never seen on a past paper before, maybe. But there it is. There it is. I didn't make it up. Possibly, 𝗟𝗲𝗲𝗲. Probability sinks into everything we do. I can Wombat, but you don't need it. So if you're thinking about doing a conversion by just reading off the scale, that would be a mistake, because we are given enough information here. Yeah, like it or not, we're going to have to do a unit conversion. Now, unit conversions are GCSE level just as they are A level. Although, obviously, at GCSE level, I've never seen one quite as perverse as this. You can't read. No, you can. Of course you can. Don't put yourself down. You watched last week. I made mistake after mistake after mistake. So let's see what you come up with. If you're a GCSE student, you're playing along at home, don't be put off by the fact it's A-level. Grab your pen, try and do the conversion, even if you don't get time to type your answer into the Discord chat. That's okay, because you can still see what other people are typing and see whether your answer is comparable. Oh, Pranav just wants to have a look and see if the number seems to be sensible. How about that? I think I can see what mistake you've made, Pranav. I think you'll be able to see what mistake you've made as we go through it. Ritva, I think you're correct. Anyone got pressure yet for me? You're going to make me work it out, aren't you? Nice. Nice. Look at these numbers. Right, now let's have a look. So I'm going to write down my 37. I'm not going to do the error parts. You've already done that bit for me. 37. And you know what I'm going to do? I'm going to write down pounds. And I'm going to write down here inches squared. And I'm doing that for a reason. I'm writing the units because I'm going to, in my conversion, cancel them out. I want to get rid of the pounds and replace it with newtons, because pascals are newtons per square meter. I'll write that up here. Pascals are newtons per square meter. Oops, that's a cube. Don't make that mistake. Oof. So what I'm going to do, I'm going to cancel out the pounds by writing 4.448 newtons divided by 1 pound. 1 pound of force is equivalent to 4.448 newtons. That's what we've been told. Yes, arcanic. You've got to be careful of that. Okay, that it is equivalent. And if you multiply something by 1, you don't change it. And if you divide something by itself, then it just equals 1. So what I've essentially done is multiply this pressure by 1. Because these two numbers mean the same thing. But it means I can cancel the pounds unit. Now, if you're a regular viewer of Physics with Keith, you've seen me do this sort of unit conversion many, many times. Now, I need to cancel 2 inches. So I need to have 1 inch, and I'm going to put 0.0254 meters. But I need to cancel a 2nd inch as well. That's another 0.0254 meters. That way, I've got inches times inches, inches times inches. I've cancelled my inches. And the unit I'm left with is the square meters. Meters times meters on the bottom. So now I grab my calculator and I type in 37, enter 4.448 times 0.0254. I'm going to square it because if I can find my square button, I'm not used to using this calculator. I think that's it. And then divide. And I get, in pascals, be careful of this, 2.551 times 10 to the 2.5 pascals. But what does it want me to convert it into? Kilo pascals. So we did some practice at this last time. Basically, I'm going to reduce the power by a factor of 1,000. So 2.551 times 10 to the 2 kilopascals. Kilo means 10 to the 3. Yeah, exactly. So this is 255 kilopascals, which I think is what you all said. Right, then. It says somewhere, plug it into the graph. Maybe that comes later. Explain what's meant by absolute zero. I'm just looking at the clock, as always. I've gone on too long, and there's a really beautiful part of this question I want to get on to. What's force divided by volume? Did I write that, Pranav? I hope not. No, I didn't. I don't know. I don't even know if that's a quantity. Don't even know if that's measurable. I'm not sure that's measurable, Pranav. Interesting question. Yeah, no. Anyway, so I'm going to try and get through this bit. So explain what's meant by absolute zero. Fine, we can talk about that. Absolute zero, the lowest temperature that any matter can possibly ever reach, cannot be colder than absolute zero. You can state it, negative 273 degrees Celsius. You can state that the particles have zero kinetic energy at that temperature. Therefore, they've stopped, so there's zero pressure exerted on the walls of a container at that temperature. This is all good stuff that you can include. Now, on some exam boards, if it's a question where they're looking at how you answer as well as what you answer, what they used to call quality of written communication questions, nowadays they tend to get called level assessed questions. Some exam boards put a star next to the question to give you a clue that if it's out of 6 marks, it doesn't necessarily mean you've got to say 6 things. Ah, there we are. Thank you, Pranav. I've learnt something. Not all exam boards do this star thing to give you that indication, though. So just bear that in mind. This is OCR. They do. I know, for example, AQA doesn't. You just have to guess which ones are level assessed. Usually they're 6 marks, but not always. Okay, so determine the value of absolute zero. You may assume the gas behaves like an ideal gas. So we've got this, this graph. With 3 minutes left, I'm sorry, I'm going to talk at you now and tell you how to do it. The first thing you do is to draw your line of best fit. And do the best you can to draw your line of best fit. Yeah, I don't mind, Pranav. I don't mind at all. In this case, it's more useful for temperature to be on the x-axis for a good reason. So anyway, you do your line of best fit. Then you calculate the gradient. You think, why do I need the gradient to the line of best fit? Because the line of best fit is in the form y equals mx plus c. And what we want is the value that x takes when y equals 0. We want to calculate what x equals when y equals 0. When there's 0 pressure. That was part of our definition of absolute zero. In order to calculate that, we have to know what the gradient is. Yes, and what the y-intercept is. Having it in the y-axis makes so the y-intercept is absolute zero. Okay. I'm sorry, Pranav, but it's not in this case. So you need to know what these two quantities are. So the first thing you do is you compute what m equals. The second thing you do, and you can do this, you can compute what c equals from that value of m. So you take a point on your line somewhere up here, preferably where some grid lines are. Don't use, this is a pro tip, don't use the points that have been used for plotting. because then it just looks like you're using the plotting points. Use some other point. If you're calculating the y-intercept, when you've got the gradient, you're plugging in a particular value of x and y, use as large a value of x and y as possible to reduce uncertainty. So then once you've got that, you've calculated your m and your c. I'll take your word for it. There's a little bit of leeway, 𝗏𝗏𝗧𝗏. Yeah, of course there is. But what you can do is, you don't want to rely on that. You can use the larger values as possible. There will be leeway because there's, it's not going to be a perfect line of best fit. But use as large a value as possible. The uncertainty is lower. Oh, okay. Yes, you are right, 𝗟𝗏𝗲𝗏. That's where it should be plotted. Absolutely right. Okay, so then you've got what your absolute zero is, which you've extracted from this graph. And then, very, very quickly, describe without any calculations how you could use that figure to determine the actual uncertainty. So, describing, you would draw a second line of best fit, which is worse than the first line of best fit, but still just about acceptable. In other words, it has to pass through all of those error bars, but not be as good as the line of best fit. Then you can, exactly, you've got the error bars there. So then you can calculate the gradient, the intercept, and then you can use that to calculate what absolute zero is with this new worst fit line. Yes, but it's not the worst fit line, because the worst fit line would be something like this. Here we go. This is the worst fit line. You wouldn't do that. So it's the worst acceptable best fit line. And then you would use that number. The difference between that number and the number you get for the absolute zero from the best line of best fit is the uncertainty in the line of best fit. But it doesn't ask you to do that. It just says, how would you do it? So you'd write in words how you would do it, which I've just said. But the last question here I thought was a really tasty question. No. Wombat, because you're doing physics back to front there. In experimental physics, you don't use expected values in your calculations. You work with the data you've got, you get a number, you get the range that number can take. So you get the value, it's at its mean value, and in this case, absolute zero, the mean absolute zero, and the error in that absolute zero, and then you compare it to what theory predicts or what a reference you've looked up predicts to see if it's within that range. Exactly, Pranav. Assume you just don't know. You're clueless. So this question here I really liked. Absolute zero was found to be this. Wow, that's wildly wrong. So compare this value to your value in CII. Explain why the values differ. This experiment is repeated, but this time the water bath quickly cools. And I'll tell you now what the answer is. I can see what the answer is. If we've got a straight line, but it crosses the x-axis at negative 390 degrees Celsius, then the whole line is shifted to the left. That means that every temperature we've measured is actually a bit colder than it should be. And that's what happens if you heat up this water, too quickly. You haven't allowed the temperature of the gas to get up to the same temperature as the water before you measure the temperature of the gas or the water. All the water temperatures are too high. If all the water temperatures are too high, or the gas temperatures seem a little bit too low, the whole line is shifted. I think I've got that right the right way round, but I've overran, so if I'm wrong, feel free to correct me in the comments. Exactly. It won't reach equilibrium if we're heating. We're making a dynamic measurement of temperature, Wombat. But the trick is, if you heat more slowly, then that measurement of temperature of the water will be closer to the measurement of the temperature of, or what the temperature would be of the gas. And it's the gas temperature that we're experimenting on, we're trying to experiment on, because it's the gas pressure that we're measuring. Gas, ideal gas. It's all about the gas, and yet we're measuring the temperature of the water. Okay. We're not anymore, 𝗟𝗲𝗲. We're finished. It's all done. So, listen, thank you very much for tuning in. It's been a lot of fun. We move on to a new topic, although I can't remember off the top of my head what it is. But we do move on to a new topic next week, so do tune in with that. If you have any questions, get on the Discord channel. Pop those questions into Discord. If I don't answer, then there's plenty of other physicists there who will answer. There's plenty of people on there now. It's a bustling hive of activity. It's wonderful to see. Share this with your friends. The best way you can help me is by liking the video, subscribing, and sharing with your friends. If you do that, more people subscribe. That helps me. If I hit 1,000 subscribers, I can embed this on my website, and so on and so on and so on. You don't want to hear me. Thanks very much, Pranav. I'm glad you found it poggers. Thank you all. Thank you for coming. Have a lovely week. Stay safe. And I will see you next Tuesday.